Hello everyone and welcome to this revision lesson on the Year 8 Electricity and Magnetism topic. For this lesson you will need to have with you your Collins revision guide that you were sent by us earlier on in the term. And you will need to have completed the pages that are listed on the left hand side of this video. What I'm going to do is I'm going to go through a few of the key points in the revised pages and then go through some answers to the questions on the practice and review pages. If you have already done those pages and already done that work, then you're ready to watch the rest of this video.
Okay, so we'll have a look at some of these ideas about electricity and magnetism first before I go through the answers. There are often lots of bits to do with electric current and stuff that can be quite confusing and quite difficult to understand, but I think the key things that I want to tell you is, first of all, that electricity is essentially tiny particles, which are called electrons, that transfer energy. That's the key thing that you need to remember. They are tiny particles that transfer energy. And what the particles do is they move, and that's what we call current. And how much energy each one of them transfers, we call potential difference, or we call voltage, either or. Okay, and this is sort of summarized in this little section here. Now what I want to do is, rather than look at these, I want to show you a circuit that I've already drawn and sort of go through this with you. So first of all, just to explain a little bit about the current. So the current in this circuit here is going to be the same at all places. So at this point here, let's say it is 2 amps. So amps is simply the amount of current that goes through each second. So this will be 2 amps here. This is going to be 2 amps here. At this point, it will be 2 amps. At this point, it will be, hopefully you're thinking 2 amps. And at this point here, it will also be 2 amps. It's going to be 2 amps all the way around. And the reason for that is because of what current is. Current is tiny charged particles. And those charged particles, they start off here in the battery and they all are going to move around and get back to here. They've all got to do that. You can't lose them somewhere. You can't mislay them. They all have to go around. If you wanted to think about something a little bit bigger and a little bit more easy to visualize, you could imagine, let's say, vans, like delivery vans driving around. All of them start off at the depot. They travel around to all the different places. And then they come back to the depot in the evening. That is the way that things have got to work, because they're actual things. So that's your way to think about current. We then think about volts as like the energy that's delivered. So here, each of those electrons or each of those charges, it picks up 6 volts. Okay, and the details of that we can leave till later on in secondary school. But let's just think of it as 6 volts. So let's say there's then 3 bulbs to go to, and they're all the same bulb. Each of those is going to get 2 volts. They each get 2 volts. Okay, so the 6 volts that goes into the electron is then handed out evenly, shared out evenly between each of these 3 bulbs. Okay, we're going to change the circuit ever so slightly, and to change the circuit I'm going to rub out this bit here. And I'm going to draw in a little bit of extra circuit up here. I'm only going to put 1 bulb in this section. Okay, so this is a symbol for a bulb. And then we come back down to here. Okay. Now I can tell you that by adding this, nothing here has actually changed. All the bulbs will have the same brightness. They're going to have the same amount of current going through. But let's have a little think about what's going on up here. Right, this bulb here is going to have a different delivery van doing the round. Okay, this one has had the 2 amp delivery van doing the round. This is going to get a different delivery van. So what's that going to get? Well, it's going to get, in this particular case, I'll tell you, it's going to get 6 amps. Okay, it gets 6 amps going through there, and over here it gets 6 amps. So what's the total at these 2 points here? Well, down here we had 2 amps going down. Down here we have 6 amps going up. So that means that coming along here we have got 8 amps. And that means that here there's 6 amps going there, 6 amps going there. So that means going through here is 8 amps. So what goes through a cell is the total of each of the different, and we call these the branches. Okay, the cell has the total of what goes through each of the branches. Now this is the depot where 6 volts are always picked up. If we're thinking delivery vans, or if we're thinking electrons, each electron's getting 6 volts, 6 bits of energy. So how much will this bulb get? Well, the electron is only passing through one particular bulb, or the delivery van is only going to one house. So all 6 have to be given to this one here. Okay, 6 volts goes through there. So this is the way that those circuits work. Let's just quickly look back over here. Okay, so first of all, this here is a series circuit. It's got a single loop, and the current is the same at all points in here. Between those 2 bulbs, whatever's provided, the potential difference or the voltage that's provided by the battery or by the current, the cell, beg your pardon, is split equally between those, assuming they've got the same resistance. In this particular case, this is a parallel circuit. So these here are called branches. Okay, and when they meet up, the current in each of the branches adds up to make the total current that passes through the cell. So 1 amp each here at 2 amps in total. But these bulbs will get all of the voltage that this parallel circuit, that this battery is providing. So let's say this battery here is providing 6 volts. These are each going to get 6 volts because they have a different current transferring the energy to them. So just a few key things then to say about components and resistance. This, I think here, this is really the key bit here. If you have more resistance, you will have less current. That's the key thing. And actually that's the clue is in this word resist. If you are, let's say you're stood at a door and there's a flow of people coming in. If you try to resist them, if you try to slow them down, if you put something in their way, then that is going to reduce the flow of people coming through that particular door because you are resisting them. And that word resistance applies just the same in electricity. Where you've got higher resistance, you have a lower amount of current coming through. So greater resistance, you have a lower amount of current coming through. There's a couple of equations, and you should know what these equations are. This here is resistance is equal to potential difference, also known as voltage, divided by the current. So in this particular case, you do the volts divided by the amps to get the ohms. Ohms are the unit of resistance. That's what this symbol here means. Volts divided by amps gives you ohms. Okay, you can also say that volts is equal to amps multiplied by ohms, which I should really write out as V is equal to I multiplied by R. We've also got this one here, the electrical power. P is equal to V multiplied by I. Power is equal to volts multiplied by current. Lots of students say, I don't know why current is I. Nor do I. I don't know either. It just is. Okay, current is I, and it's measured in amps. And there's a few things there that could easily confuse you. Okay, they've confused me for many years. I don't know why, but that is the case. Volts is V is voltage. That's easy. P is power. That's okay. Measured in watts. What is the unit of power? Yes, what is the unit of power? That's okay. Current I amps. you know, you've just got to learn it. You've just got to learn it, that current I amps. You've just got to learn it. If we have a look at this circuit over here, we can do a couple of calculations. So first of all, the power for this bulb, power is the volts times the current, which is 6 times 6, which is therefore 36 watts. Okay, a very powerful, very bright light bulb. Okay, down here, this is going to be, power is going to be potential difference multiplied by current, 2 times 2, which is only 4 watts. So this is 9 times brighter, this top bulb, than this one down here. We can also work out the resistance. Let's do the resistance of this one. Resistance is equal to the potential difference, the voltage, divided by the current, which is equal to 2 divided by 2, which is equal to 1 ohm. Okay, so that's the resistance of this particular bulb. And actually, this bulb up here is also 1 ohm. Let's take a little look at currents. These are really quite straightforward. Currents. Magnets. These are really quite straightforward things. You need to know the 3 magnetic materials: iron, cobalt, and nickel. Aluminium is not magnetic. Copper is not magnetic. These are those 3 magnetic materials. We know that magnets have north and south seeking poles at each end. When magnets are brought near to each other, they will either attract or repel. If you have different poles, north to south, it will attract, it will pull them together. If you've got similar poles, it will repel, they will push apart. And you should know the shape of the magnetic fields. Now, I like to think of these as like if you've got just one magnet, I'll just draw one magnet here. There's a north, there's a south. I like to think of that as like a beef burger, and then we've got the burger buns around it. And that's, I mean, it's really quite silly, isn't it, to talk of it like that? But that's the way I like to think of it. Magnetic field lines, they go from the north, they come out of the north, and they go into the south. So you should follow them round. It's coming out there, and going in there. Out there, and going in there. Don't make the mistake of having that go round and round in circles, because that's not correct. I think the rest of this page 102 and page 103, is fairly straightforward for you to read through. Key thing here with this bit, if we electrical currents can create magnetic fields, which is really quite brilliant, and it's used in loads and loads of ways to do loads of useful things. So you should know about that. You can make it stronger by putting more coils in, by having a greater current, or by putting a core. So by a core, we mean actually putting like a lump of metal, cylinder of metal in here. Okay, if we put a cylinder of metal in here made of iron, that is going to make that magnet an awful lot stronger. Okay, so let's go through these questions here. So a bar magnet, what should that look like? Well, we don't need to draw anything fancy in 3D. We just draw a bar like that, put a north, put a south, and then we're going to have magnetic field lines. I said earlier on, it's a bit like a hamburger or a beef burger, and they're going to look like this. Okay, so there's our top burger bun. And the lines, the magnetic field lines, should come out of the north, go into the south. Okay, that's the way they should go. So that is a bar magnet with magnetic field lines. So Andy and Catherine are building a simple electromagnet, and they want to increase the strength of it. Which would be the following would be the ways to increase the strength. More turns on the wire. That would be the case if you have just one turn, it's very weak. But if you've got lots and lots of turns, it's nice and strong. That's good. It says use copper wire or use thicker wire. Not necessarily. We'll go for add an iron core. That will make it stronger. So we fill the electromagnet here with a lump of iron. And essentially what that does is it causes these magnetic field lines to get focused within the in the solenoid, in the coil. So that makes it stronger. Also by increasing the current, that would make it stronger. Now, these two here, they are not completely wrong, but really it should be about increasing the current. Generally, if you use thicker wire, you can get a larger current. And if you were using some other wire and you started using copper, that would also slightly increase the current, but this really would be the key idea here. Catherine wants to know why an electromagnet can be more useful than a permanent magnet. What should Andy tell Catherine? Well, I guess the key thing is this: you can turn it on and off. And so that makes it very useful because you can switch it on, pick up something magnetic, and then switch it off and drop that magnetic thing. Okay, let's have a look then at question 3 just here. A parallel circuit shows 4 ammeters with 2 identical bulbs. If the first ammeter reads 4 amps, so this one here reads 4 amps, what would each of the other ammeters read? So this one here is 4 amps. This one here is also 4 amps. This one here, because these are identical bulbs, this will split, and so we'll have 2 amps here and 2 amps there. Personally, I don't think it's a great idea they've called these A4 and your answer needs to be 4A. I think that gets a bit confusing. You could just call this one A, B, C and D, and that might make a little bit more sense. Okay, what current will flow through a 60 watt bulb with a voltage of 230 volts? So what we are told here is we're told that the power is equal to 60 watts, the voltage is equal to 230 volts, and the current is what we want to know. So we're going to use the equation P is equal to I times V. And so what we're going to do is we're going to put the numbers in. 60 is equal to I times 230. So I will be equal to 60 divided by 230, and I can't find my calculator, otherwise I would do that. Oh, I can. Beg your pardon. Here we go. 60 divided by 230, and you should have an answer of 0.26 amps. Calculate the energy in kilowatt hours transferred if the bulb was on for 200 hours. Show you're working out. Okay, so energy is equal to power multiplied by time. The power here is equal to 60 watts, but we need to divide that by 1,000 to get it into kilowatts. We then need to multiply that by 200 hours, and we've got kilowatt hours. The H stands for hours, so we can keep that as hours. So 60 divided by 1,000 times 200 gives us an answer of 12 kilowatt hours. Okay, so now let's do the review questions on page 112. So which of the following elements are magnetic? Only one of them, cobalt, is the magnetic element here. Okay, which of the following circuits will work? Well, first of all, this circuit here won't work because this one will add 1.5 volts and that will take away 1.5 volts. So overall, this is worth 0 volts and nothing will happen. This circuit won't work because there's a break there. So no current will be able to flow across this gap. This circuit won't work because this is a voltmeter. This is not a cell, and so there's no energy source. So this is the circuit that will work. Okay, then we've got a question here about a relay switch. It enables a small safe circuit to be switched on, and in doing so turn on a more dangerous circuit with much higher voltages. So we've got a 9-volt circuit here, nice and safe. You could use this switch here with your finger quite safely, no problems. But 10,000 volts, that is going to zap you. So what will happen to the electromagnet when the switch is closed? So this electromagnet becomes magnetic, becomes magnetic, or we could say it creates a magnetic field. That would be a better way of saying it. It creates a magnetic field. Explain what will happen to the armature once the switch is closed. So this is the iron armature, and the crucial thing here is it's made of iron, so it's a magnetic material. It's on some kind of a pivot, so it will be attracted. Okay, it's going to be attracted to the magnet. That is always the case whenever you've got an electromagnet and an iron material. When the electromagnet becomes magnetic, any magnetic material such as iron will be attracted towards it. So it will be attracted to the coil and complete the circuit. Okay, well, I hope that this has been a useful and helpful video for you in going over some of those key ideas about magnetism and electricity.